traditional electronics. How embracing disorder in nanotechnology may lead to quantum machines. David Awschalom, University of California, Santa Barbara.
On November the 9th, 1989, I was in the IBM Watson Research Center in Yorktown Heights, New York. The lab was at a virtual standstill as people listened intently to the developments in Germany.
Well, thank you very much. And I'd like to thank the organizers for giving me this extraordinary opportunity to chat with you this morning about some scientific discoveries that are leading to what may be very much disruptive technology and might in fact break down the walls of traditional electronics. So what are some of these walls in electronics? Well, a lot of us, I think, see them every day. One of them is heat and power. We're reaching incredible power dissipations now in our current technology, where the CPUs running in your laptops are approaching really extraordinary densities of large-scale systems. And it's hard to see how that's going to continue just based on the limits of real materials. So that's one challenge we have. And another challenge that we have in this business is fabrication. Over the last 5 decades or so, as we really try and craft our technologies and make bits smaller and smaller and smaller, there's a really interesting way to look and see how we store information. And that's the number of atoms that are used to store one bit. And if you look at this plot, you can see where we're going. In the next couple of decades, maybe even in the next decade and a half, we're going to reach a regime where just a handful of atoms are going to be needed to store one bit of information. And that's a real problem when you're trying to build current devices. And why is that the case? Well, we've gotten really, really good at making perfect devices. Today, Intel alone makes 5 billion transistors every second. And for those of you that are awake enough to do a little math, you probably realize that's 20 million transistors per person on the planet each year. It's an enormous machine, but it's also a challenge to keep that going. So those are two walls. Another wall is to look carefully at what limits order. Well, we seem to have a real drive to make order out of disorder at all different length scales, and yet nature has a very different approach. Nature tends to embrace disorder and make remarkably complex structures using defects and disorder. And you can see that even on landscapes, from man-made shrubbery, where people work disturbingly carefully to make perfect shrubs, to how nature and swamps form very intricate patterns. But even in our technology, the same drive for order persists. We can see our man-made technologies trying to craft rectilinear order in perfect circuits in 2 dimensions. And yet, in parallel, biology and nature has worked to create a beautiful computational machine that runs at a fraction of the power of our technology, embracing disorder and order over different spatial length scales to make a machine that can not only compute, but it can also learn. So maybe we can learn from that. And what happens as we try and push things smaller and smaller and try and hang on to perfection? Well, we have problems, and we have 2 problems. The first is when you try and make things very small, disorder becomes a very important issue. In very small bits of matter, just moving one atom a little bit left or right can completely change the properties of a material. And not only does that happen, but the rules of physics change as we go to small length scales. How many of you are familiar with quantum physics? Sure. That's because we don't experience it in the everyday world. But as you go to very small length scales, quantum physics is a dominant rule, and that changes everything. At length scales that we're familiar with, like a bee, going down to the eye of the bee, to a bit of bacterium on pollen, to a virus on a bacterium, to DNA itself, simple changes of atoms and the movement of electrons in these systems obey these quantum mechanical rules. And it's a very different world indeed. So our technology has been driven by our world, the macroscopic world, length scales, our length scales. We build technologies with perfect silicon, we put electrons on devices, and we shuttle them on and off, 0 and 1, a binary technology. And it works very, very well. But as I've just been mentioning, maybe we can think a little differently. Maybe we can stop fighting the need to make things perfectly and think about using defects, using damaged materials, using impurities to control a different property of the electron that drives our technology. So most of us are pretty comfortable with the fact that electrons carry charge, and we move that charge around in circuits to build devices. But electrons have another property. They have a quantum mechanical property, which is spin. An electron has a spin, much like the Earth spins around its axis, the electron spins around its axis, but this is a quantum mechanical property. So it means the spin doesn't simply go clockwise or counterclockwise, It can be in a combination of these two states, indistinguishable, both left and right and everything in between. And it's a very unusual type of state, and it's something we don't see because it exists at very small length scales. But can we harness that quantum mechanical property? And imagine building a technology where you have arrays of these quantum mechanical states, and you build a technology where you don't move the electron, you don't generate large amounts of heat, and you can open the door to immense storage and computation. And that's what I want to talk about a little bit this morning. And one way to think about the quantum world is imagining what things would be like if we could bring those quantum properties into our world. And as we heard earlier in the introduction, physicists like to take a step back and try and imagine that they understand these things. And you have to work with me on this. So we think about the quantum world. One way that I like to imagine is think about a classical factory. Imagine we could make basketballs that were quantum mechanical. Well, in a classical ball factory, you can make, much like our recent election, red and blue states. I'm going to stop the analogy there. We'll call them equal. You can make a red one or a blue one, and all of the information is contained in that ball, and we're pretty comfortable with it. But in a quantum factory, there's a third option that's available. It's a ball that's both red and blue at the same time. So that doesn't mean purple. That means red and blue at the same time. It's a very unusual type of ball. So what does this mean? Quantum states have two unusual properties. So here's our factory, and we make a quantum ball. One of the unusual aspects of this quantum ball is when we look at the ball, it could be red. And by looking at the ball, we force it to be either red or blue. We generate another ball from our quantum factory. We don't know what it is, but when we look at it, we force it to go into one of these states, either red or blue, in this case blue. So the act of observing the ball affects its outcome. And that leads to what is one of the most mysterious and powerful properties of quantum physics, which is entanglement. And that really defies our notion of how we work in the everyday world, which is that we can take two quantum balls and make them entangled, which means that the information in these entangled states is shared between the two and in the interaction between them. It's very non-intuitive. And what that means is looking at one of those balls will affect the other, even though they're separate objects. And that has dramatic consequences. If I take these two entangled balls and I put one of them on Earth, and I take the second one, and I put it on Mars, just like that. And I haven't looked at them yet. The fascinating thing about the rule of quantum physics is that once I look at the ball on Earth, I've instantly changed the one on Mars. Yes, I see a look of disbelief. And yet it's true. So it's a very interesting phenomenon. Looking at one instantly changes the other. And they're independent of distance. It's a relationship without a physical connection. It's a very, very different type of science, and one that's pervasive at the atomic level and very uncommon at our level. And if it was common at our level, we'd be living in a very, very different society. So how can we try and harness this idea of quantum interactions and build a real system, build a technology based on these unusual rules of nature? We can think about a different type of semiconductor. While all of us have worked pretty hard to craft silicon, another very common material on the planet is carbon. And historically, one of the most common aspects of carbon is diamond. I'm guessing some of you in the audience have a diamond. Okay. And if you have diamonds, you probably know they come in different colors. Why are they in different colors? It's because they're defective. And for those of you that purchased an expensive colored diamond, I'm sorry. Still nervous laughter. So why is some yellow? Well, nitrogen is an impurity, and otherwise a perfectly clear carbon lattice. Nitrogen makes it yellow. If boron is put into a diamond, it looks blue. And a pink diamond has both some nitrogen and some missing carbon atoms. Very nice type of diamond, even more defective than the others. So we can try and fight these defects and look for very, very beautiful systems, or we can use them, embrace this type of disorder, embrace these type of defects, and build a new technology that's defective. So let's look at this pink diamond, a missing carbon atom and a nitrogen atom nearby, and think about, well, maybe damaged semiconductors aren't so bad. And maybe we can think about this, semiconductors are a bit like people. It's the defects that make them interesting. Some of us more interesting than others. It's not that funny. So as you look into a diamond lattice, as you can see in this animation, you'll see a lot of carbon atoms in blue. And if you look carefully, in addition to the blue, you'll see some red atoms that are sticking around that are defects, these nitrogen atoms. And occasionally you'll see some white spots there that are missing carbon atoms. And the amazing thing that nature has done for us in creating these defects is that nitrogen and that missing carbon atom come together, they form an enormous type of trap that holds one single electron. One single electron whose quantum state can be manipulated either with light or with electric or magnetic fields with extreme precision. It's a very surprising discovery that defects, in fact, can be the answer to building single particle electronic systems. And you can do this in the laboratory. Here's a diamond chip. You can see it's covered with some nitrogen, so it looks a little yellow. If we connect some wires to it and apply electromagnetic radiation at gigahertz frequencies, we can actually take that one electron, manipulate its quantum states into the different superpositions of states, and study it at very high speeds. One single electron in one single atom. Very, very difficult to do with conventional technology, but it turns out you can do with this technology. So you can take a beautiful piece of diamond and systematically destroy it, putting in defects, thousands of them, and suddenly you have an array of quantum states that work on the desktop. So what do you do with something like this? And this is the challenge that science has right now, but I wanted just in the last few minutes explain why people are working so hard to extract this physics and use it for technology. Today, if you want to increase the power of your laptop, what do? You take a state-of-the-art CPU that has 700 million transistors, 700 million, and you add a second one, another 700 million transistors. You spend a little more money, and what you've done is by doubling the number of transistors, adding these two chips together, you've doubled the computation power of your machine, which is nice. But quantum machines are very different. Let's not take 700 million transistors, let's take 10,000 equivalent transistors, these quantum bits, these spins, just 10,000 of them that are all interconnected. And let's just add one transistor, not a chip, just one transistor to it. Adding one device doubles the power. But if we took this 10,000 and we added another 10,000, we would have a machine that's 2 to the 10,000 times as powerful. So that's an enormous number. That's essentially the number 1 with 3,000 zeros after it, almost infinity. It's an extraordinary change in technology, a massive change in complexity. And it works because quantum information, just like these entangled balls I talked about earlier, the interactions and the informations are all shared with each other. In binary computers, most of our technology works like a telephone directory. There's a name and there's a number, and there's a big list. And every name has a 0 or 1. In a quantum technology, it's a relationship network. Information is shared between everyone, a little bit like Facebook. If you add one more person or one more bit to the system, one bit doubles the number of relationships. And that can lead to interesting dynamics, sometimes good, sometimes not so good, sometimes interesting, sometimes frightening. But time is short, so I'm going to leave that alone. And I want to spend the last few minutes and explain what we could do with a machine that has so much power and an almost infinite number of storage bits. What could you do with a machine like that that you could hold in your hand? Well, people talk about big data, but the point of a machine like this is you can go well beyond this type of application. You could think about designing molecules from first principles and simulating them completely to know what their impact is. You could design pharmaceuticals to target particular illnesses, targeted drugs that you could design, again, from first principles, from basic quantum mechanics, and describe their operation perfectly. You could build what we call quantum materials, materials like superconductors, and design them in principle that might work at room temperature. A room temperature superconductor would change everything, from transportation to energy transmission to communication. And even synthetic biology, where you could design and construct biological parts for a variety of different uses. So a lot of us are driven by this field because of its impact in the future. And as we heard a little in the introduction, it's not absolutely clear where this is going. But it's going very well and it's going very quickly for the reason that it turns out these rules of quantum mechanics can actually be engineered at this point and engineer them into networks and larger systems to address fundamental questions on the origin of the universe. How does quantum gravity fit into the universe picture? What are the limits of measurement? How big can an object be and still behave quantum mechanically? That's actually a very interesting question, both for science and for philosophy. Maybe we can even map the brain. It's a pretty complex problem. Hundreds of millions of neurons that are completely interconnected. How is that going to work? Can we model the way that we think? Can we understand creative thought? So there's a lot of potential with a machine like this. It's a bit taunting to think of a machine that can store as much information that exists in the universe in a relatively small volume. And I think it's up to a lot of people in the future to imagine what a machine like this might be used for and how it can best be employed. But it's clear when a machine like this comes, and it will come, it will have a very big impact on science and society. And maybe one of the most important ways that we think about that are important to derive this type of technology is to train a new generation of students. Yes, I know. Subtlety isn't the forte here. We need to train a new generation of engineers, but in this case, quantum engineers, people that can normally take these disparate areas of science, engineering, mathematics, experimental science, and theory together to drive this technology forward. So thank you very much.